So if you're looking for something and the link doesn't work, then go to the site. If you're still having problems, let me know. Is this a bit loud? Sounds crazy. I guess I could just put it further down. Okay. Okay, and some of you have also asked about changing the assignments to Thursday. You prefer Thursday or Tuesday? Okay. So I guess next time I can put them all on Thursday. The reason why I switched the assignments from Tuesday to Thursday is because we have a holiday coming up, Veterans Day. And let's see. So these assignments, let's see. So assignments 4, 5, 6, 7 are all due on Thursdays. Then I give you an extra couple of days and I switch it back to Tuesday because of Veterans Day. Should I switch this back to the Thursday before or just leave it? So this kind of gives you an extra 5 days in between. Yeah, so we just leave it as is then. And then that brings us up to Thanksgiving, obviously on the Thanksgiving weekend. I make it a Tuesday again. And then finally in the last week it's a Thursday again, which gives you extra time again. I don't want to take it into the reading and review week because you're supposed to be doing other stuff. That work out for everybody? Okay, great. So today what we're going to do is we're going to come back to fisheries problems or harvesting problems more generally. We've worked with the cohort model. We've worked with harvesting the logistic model, harvesting a cohort model. And then we come to an age-structure population model. And so I'm going to present the age-structure population today. And then on Tuesday, we're going to tie all the harvesting stuff together in a more detailed fisheries or harvesting model. But today we're going to talk about matrix models for modeling populations where you're taking into account detailed age structure. And so, as we had talked about in the last few lectures, if you want something a little more refined than just talking about juvenile and adults, which is what we were doing, to keep it simple, two stage classes, you might want to have more structure. And a very popular model is to consider an age structure model where x1 to xn all represent individuals in n age classes, age 1, age 2, age 3. Depending on the organism on hand, those age classes may be annual classes, which is suitable for large mammalian herbivores that live for 15, 20 years. In some cases where you even longer-lived species like elephants and whales, people will have age classes every 3 years or 5 years. And in fact, we're even going to talk about modeling forests where you look at the age of trees, and trees can be aged by counting the rings when you cut a tree down. Of course, that's highly destructive. So very often people can age trees by taking a core out and then looking at the rings. And in that case, if you're talking about trees, you might have 5-year age classes, or you might even go to size classes. And in size classes with trees, you talk about the diameter of the tree at a particular height. And then you divide things by size class. Typically with a lot of animals, we do use age class, but for fish, again, it may be size class. Some of you may not know this, but you can actually age fish by looking at the ear otolith, which is a bone in the ear, and it also has growth rings, and it has a strong seasonal pattern. So in some long-lived fish, there are fish out there that live for 20, 30, 40 years. If you catch fish like that, you can actually tell their age. So imagine we have a vector u, and it has n elements, x1 to xn. And as I said, this could represent individuals in the first age class up to the nth age class. When people study things like Drosophila and rear them in the lab, the age classes may be days or weeks, and the same if you're rearing something like mice. Now, everything we've done in terms of manipulating vectors is done in exactly the same way, irrespective of whether it's a two-dimensional or n-dimensional vector. So we can write down an n-dimensional square matrix like this, and we can define addition. Vector addition is element-wise. If we're multiplying a vector by a scalar, then we just multiply every element by that scalar. And most importantly, if we're doing multiplication, you can multiply an n by n matrix by an n by 1 vector to get an n by 1 vector. So it's the first term times the first element times the first, the second times the second, the third times the third up to the final one, and you add them all together, and you get the first term there. Then to get the second element in this vector, you take the second row, and again, times the column, a21x1, a22x2, and so on. Okay, any questions about that? Now, one of the things that we had talked about is finding the determinant of a matrix. So it gets a little more complicated in two dimensions. And you might take a look specifically of how to do it for a 3 by 3 matrix. You don't have to know how to do it for an n by n matrix. But all you have to know is that by taking a suitable combination of elements and multiplying them together and adding them or subtracting from one another, you can work out the determinant of an n by n matrix. And there are probably programs online that will do that. So if you just say, find the determinant of a matrix for me, there's probably something out there where you can enter the elements and it'll give you the determinant. So you have to know that you can do it. You have to know that it's important to do it because it helps you to solve the equation a times x equals some vector b. Then the solution is x a to the minus 1b. So if you can find this matrix, which is the inverse of a, then all you have to do is find the inverse of a and take that inverse and multiply it by b, and that'll give you your answer. And you can only do this provided the determinant of a is not equal to 0. The determinant of a is always a number. Okay. So now we're going to come to the Leslie model. at the heart of the Leslie model is this very simple relationship. xi plus 1 at time t plus 1 is equal to xi at time t. And in the Leslie model, xi at time t is number of individuals aged I at time t. In a lot of populations, all the individuals are born within a narrow time period at a particular time in the year. So if you look at deer out here that roam the Berkeley Hills, how many of you have deer come visit you in your garden? So it's quite remarkable how many there are. And then at a certain time of the year, you'll see females have young. And so it's a seasonal process, and individuals are born within this window, and so they form nice little neat cohorts. And so this model works nicely for a seasonal situation where every year at a particular time the females reproduce, and you can have a look at how many new individuals you get, and how many individuals were born a year before, and how many of them survived, or 2 years before, or 3 years before, or 4 years before. And so SI is the proportion that survive from age I to I plus 1. And if you remember, SI was equal to, how did we calculate SI in terms of the LIs? LI is the number of individuals that survive from age 0 up to a particular age, from birth to a particular age. So how did we calculate SI in terms of LI and LI plus 1? SI was equal to? Okay, yeah, LI plus 1 over LI. So it's the proportion of LI that made it to LI plus 1. LI plus 1 is a smaller number than LI, so SI lies somewhere between 0 and 1. So typically it's not 0, and it's not 1, it's smaller than 1. If it's 0, then everybody dies. So then you would stop there. So you can say this equation applies if I have I going from 1 to n here. So that means I have n age classes. Then this equation will apply for I equals 1 up to n minus 2. So if I've got newborns, if I is equal to 1, then the 1-year-olds become 2-year-olds, the 2-year-olds become 3-year-olds, the 3-year-olds become 4-year-olds. So we've got 1s becoming 2s, 2s becoming 3s, and so on. And this says that n minus 2 becomes n minus 1-year-olds. But this equation doesn't necessarily hold for the final age class. If I were to say it held for I equals n minus 1, then I would say n minus 1 becomes age n. And then what happened to the n's? Now, if Sn was 0, this would be fine if we got to n minus 1. But if I've got this age class, this final age class, and they don't all die, then what I can do is I can say this final age class, instead of being n-year-olds, is actually any individuals that are age n or older. So this holds for I equals 1 to n minus 1. And then if I say xn at t are number of individuals aged greater than or equal to n, then I can say that xn at time t plus 1 is equal to Sn minus 1, xn minus 1 at time t. So this would be this case with I equals n minus 1. But now I've still got some individuals aged n from this time, and I allow a proportion of them to survive so that they're no longer aged n, but they are in the class age n or older. If I don't do this, then I have to keep going. And I have to keep going until I get to some point where I say Sn is 0. So I can only stop this process in two ways. The one way is to say I finally reached an age where Sn is 0, or I can interpret a final group as age n or older. Everybody understand that? Okay. If I want to say keep going until Sn is 0, then I might have a very big model. But sometimes I can say I'm going to lump all individuals, like in the human population, I'm going to lump everybody who's 100 and above the same. Otherwise, I'm going to have to go 101, 102, 103, up to 120, 100, whatever. And it may turn out that there's one person who's age 120, and I don't want to say to them, you're going to die this year. You have to, because my model says so. So then I'll do it by writing out the model in this way. So this is how we terminate the system for the final equation. But now what about, how do we get newborn, how do we get 1-year-olds? So this doesn't tell us how to calculate x1 at time t plus 1. Individuals who are aged 1 at time t plus 1 must be newborn at time 0. So how do I do that? Well, I can write it like this. x1 at time is equal to s0, x0 at time t, if I say x0 at time t are a number of newborns. So but how would I calculate the number of newborns in terms of the rest of the population? How would I calculate this x0 if I had a life table? So here's Li, Bi, I, I'm going to go 1, 2, 3, 4, 5. How would I calculate this number of newborns? So I've got some entries here. And specifically, this is B1, whatever that value is. This is B2. This is B3. So there'll be a series of numbers in there. How would I calculate the newborns? What do the B's mean? What are the B's? Yeah, so it's a number of progeny born per adult, or sometimes if we're just doing with females, it's a number of female progeny per female. If there's a 50% sex ratio, then I can just change that to the number of young per adult. If there is a skewed sex ratio, which happens, then I have to be a little more careful. So x0 at time t is equal to sigma I equals 1 to n, bi xi at time t. Everybody agree with that? Everybody understand that? So B1 may be 0 if they aren't sexually mature, and B2 may be 0 if they aren't sexually mature, in which case these terms would be 0 for I equal 1 and 2. But no matter, in general, we're adding up the number of young produced by each individual, that's 1, the number of young produced by each individual, that's 2, up to n. And so you get this term over here. So therefore, I could write x1 at time t plus 1 equals sigma I equals 1 to n. So an I over here. Bi xi at time t. Then I could say x2 at time t plus 1 equals s1 x1 at time t, up to xn minus 1 at time t plus 1 equals sn minus 1, sorry, sn minus 2 xn minus 2 of t. And then I could say xn at time t plus 1 equals sn minus 1 xn minus 1 at time t plus sn xn at time t. Any questions about that? Yeah?
So, those two equations you have at the top, are they giving us different things, or why don't you just do bi for x1?
Well, so if I go to this equation here, x1 at time t plus 1 is equal to s0 x0. Then I said, but x0 can be expressed in terms of x1 to xn. So x0, I don't need it, because I can express x0 in terms of x1 to xn. So I only have to keep track of n things. I don't have to keep track of x0 as well, which would be n plus 1 things. I can always construct x0 from this, but I only have to keep track of n things. So I could write this as x at time t plus 1 is equal to L times x at t, where x is this vector. So for x, I'm writing a vector x1 of t up to xn of t. So if I adopt this notation, then I can write this equation in this way, provided L is the structure of, oh, sorry, I left off an S0 there. I left off an S0. So it's S0, x1, S0, x2, S0, xn. Well, actually, just S0, B1, S0, B2, S0, Bn minus 1, S0, Bn. And then over here I have an S1, 0, 0. Then I have a 0, S2, 0, 0. Then finally I get 0, 0, and I get an Sn minus 2 here and a 0 and a 0. So I've got another column here, which I haven't explicitly shown. And so that would be in the third column from the end. And then 0, 0, 0, Sn minus 1, Sn. Now what you should notice here, and maybe I can get another color. Is that this row is filled with elements. This diagonal has a first term, then it's filled with zeros, and it has a last term. And then this off diagonal, which is the diagonal element just below the main diagonal, is filled with elements. Then that's 0, and that's 0. So you see it has what's called a very sparse structure, where almost everything's 0, except for the first row, the off diagonal or lower diagonal, and then this one over here is a special one. Why is that one non-zero? Why is Sn not 0? Yeah?
Is that the point where the individual stops reproducing it?
No. It's an S, which will give you the clue, because S is always for survivorship, and B is for reproduction. So at the back there, you're reading something else and you're not paying attention. Why is Sn 0? Maybe you know. Please put that away. Do you know? Anybody?